Alrighty. Looks like pretty much everybody is here. So we can get moving. Oh, let's see. We're gonna do this and that and that. Okay. Of course. So as promised, this week we are going to learn two sections. Today, we're going to talk about section 7.3, which is on Trig Sub. And we did a pretty thorough introduction to this last week, so I'm thinking you guys will not have too hard of a time with this, at least when it comes to the basics. But there are some parts to this, excuse me, that I haven't shown you how to do. There are some subtleties that we haven't encountered in the types of examples we've looked at. So we're going to look at those. And then, of course, next Wednesday, we're going to be talking about partial fraction decomposition. And I think I did this with my other class, but I don't remember doing this with you guys. So if you could, just give me a thumbs up react if your pre-calculus class did talk about partial fraction decomposition. They're supposed to. So it's a part of the curriculum in all of them, but I've noticed a pattern. Not one? Hot damn. Okay. That's not terribly surprising. Usually one or two people, I would think, but okay. All right. Well, don't worry about that for now. Today's all Trig Sub. So we introduced the setting in which you would want to do Trig Sub, the kind of motivation. Square roots loathe addition and subtraction. Things like this. And this are actually pretty hard to deal with. This is definitely not 1 minus x. This is definitely not 1 plus x. And this is very much not x minus 1. So what do we do? When our integral has an expression like that, but doesn't have the piece we need for U sub. Right, if you have a square root like one of these, sometimes you can U sub your way out of it, yeah? I could ask you to compare the integrals so I'll call this integral A, and I'll call this integral B. The integral a we can do pretty easily. This fellow, we can u sub our way through this thing. Because of that x upstairs, if I make this substitution, the differential dz is 2x dx. I have an x dx right here. So a would become 1/2 integral 1 over the square root of z dz, which is manageable, right? That's integral z to the negative 1/2 dz. And so that's going to be, we add 1 to the power, divide by the new power. That's 2 square roots of z plus c, or 2 times the square root of x squared minus 1 plus c. That's not too bad. But this guy, you can't do that substitution because he doesn't have the x upstairs that you need for the differential. And b, we can't get away. And in fact, there's no similar u substitution, at least not one that I'm aware of. I did just kind of make this up on the spot, but I'm not aware of any similar substitution that will crack the integral b. And this is where trig sub comes in. Nice thing about trig sub, like we talked about last week, it's a backwards substitution. So instead of saying z is some mix-a-mash of the old variable x, I'm going to say x is equal to sine theta or sine theta or secant theta or tangent theta, which means that I'm just going to be plugging in for dx. I'm not going to be like hunting around for the appropriate piece that I need to group with dx for my differential. Oh yeah, you're right. You're right. This still should be a 1/2 here. I was being sloppy there, and this would cancel. Yeah, you're right. Good catch. Yeah, very good catch. So the 1/2 that came from the differential should still be out here in this step, and then when I integrate this, I'll get the 2 and the 1/2 will cancel, so it should just be the square root of x squared minus 1. Yeah, very good. Okay, but the point is, without this x upstairs, this substitution can't be done, or at least is much, much harder. Without this x upstairs, we need some other attack. So the integral b, what I'm actually going to do here is let x be secant theta. Right? So in the integral b, because I don't have the piece upstairs, I need to sneak through this with a u sub. I'm going to try the trig sub. We talked about why we do the trig sub last week, because this thing, x squared minus 1, if x is secant theta, secant squared minus 1, that's one of your trig identities. That's tangent squared theta. So you'll be able to get rid of the addition and subtraction underneath the square root here by making this substitution and applying the appropriate Pythagorean identity. If x is secant theta, then dx is secant theta tangent theta. So we're going to do the integral b continued. Oh shit, this should be the dot, that should be the apostrophe. No. So since x is secant theta, the integral b, I'll copy it down here, is 1 over the square root of x squared minus 1 dx, becomes the integral of 1 over the square root of secant squared theta, that's x squared, minus 1, times secant theta, tangent theta, and there should be a d theta here, I'm sorry, d theta. So is everybody seeing how this integral becomes this integral under this substitution? And I usually do like to put these in my little box. There's another piece that I usually add to that little box in an indefinite integral. That's one of the details I haven't shown you yet, and I'll be showing you exactly what I mean in a little bit here. But for now, I just want to make sure we're comfy with how the integral transforms. So you see why x squared is secant squared theta. If x is secant theta, you square both sides. X squared is secant squared. Make sure you use a different variable here, right? I'm always going to use the variable theta if I can. That's the most natural variable for me to use as the argument or the inside of a trig function. But don't ever say x is secant x. That shit doesn't make sense. So the square root becomes secant squared minus 1, and dx becomes secant theta tangent theta d theta. And notice again, like I said, you don't have to go hunting around for your differential. You just plug it in. It's actually easier than U sub. Questions about where any of the pieces in this integral come from? Okay. So then according to the second Pythagorean identity, secant squared theta minus 1 is tangent squared theta. So that's the square root of tan squared theta downstairs, and then secant theta tangent theta d theta upstairs. Square root of tan squared is tangent, so this is secant tangent over tangent. And if you're thinking carefully, you should be like, but wait, John, the square root of tangent squared isn't tangent. It's the absolute value of tangent. It depends on whether tangent is positive or negative. And I say, okay, yes, but this is Calc 2. For now, we care more about you guys getting the mechanics down than we do about those little details. So if this were a definite integral, we would need to make sure that we're in the appropriate interval for theta values so that the square root of tangent squared really does simplify to tangent. In other words, if your bounds were like 0 to pi over 3 or something, that would be okay because tangent is positive there and the absolute value of tangent really is tangent. If your bounds were like negative pi over 3 to 0, then this would actually need to be a negative tangent. But we're not going to stress about those details at this level. Every time I give you a definite integral like these, I promise it will be such that the square roots and the square of the trig function can cancel. And then the tangent from the differential and the tangent from the denominator eat each other up, and we end up with the integral of secant theta d theta. And you can see, of course, why we spent the last week studying trig integrals if we were going to do this week. What is the integral of secant theta? Who remembers that one? Very close, Maggie. 1's got it there. Natural log of secant plus tangent. And yeah, there is an absolute value. So this would be the natural log of the absolute value of secant theta plus tangent theta. Okay. So now there's just one question. I asked an integral that came in terms of x's, and I get out an answer in terms of the variable theta. And it's not as simple in this context to go back to the original variable. The nice thing about this substitution, where you're doing the backward substitution, x is a function of theta rather than theta is a function of x, is that plugging in for the differential is super simple. The bad thing is that when you get to the end and you have to go back to your original variable, which again, you only need to do if you're doing an indefinite integral, but that is what we're doing here, is that going back to the original variable isn't super simple. If x is secant theta, then this piece is going to be an x. But what is tangent theta? It's not as obvious. So what you're going to need to do at this last step here on the indefinite integrals that you solve using Trig Sub is draw a triangle. And that's why we had you practice this skill so much in trigonometry. So you draw a right triangle with inner angle theta. Doesn't matter which angle you pick to be theta, as long as it's not the right angle. I usually draw it like this. If x is secant theta, then I can think of cos theta as 1 over x, and that's always going to be my adjacent over my hypotenuse. So I label my adjacent side as 1 and my hypotenuse as x. And then I use the Pythagorean theorem to solve for the right-hand side here, the missing side. So this squared plus this squared equals this squared, means that this guy is equal to the square root of this squared minus this squared. This I usually tuck into my substitution box right at the start if I'm doing an indefinite integral. So that's the little extra piece that I usually add to my substitution box. If it's a definite integral, I change the bounds there. If it's an indefinite integral, I usually tuck this in there. That way I don't have to do it at the end. But from that triangle, you can read off the sine of theta, the cos of theta, the secant of theta, and the tangent of theta, whatever you need here to go back to your original variable. So the natural log of secant theta plus tangent theta is the natural log of, what's secant theta? That's the hypotenuse over the adjacent, that's x. What's tangent theta? That's the opposite over, the opposite over the adjacent. That's the square root of x squared minus 1. Oh, no plus c's here, right? Yeah, sorry. So then the integral of 1 over the square root of x squared minus 1 dx is equal to the natural log of absolute value x plus square root x squared minus 1 plus c there. Okay, and this is trig sub in all of its bloody glory. It's not too bad. It's really not too bad. The mechanics of the substitution, the work that you do in the integral, is actually, I think, a little bit simpler than u sub. Less of a puzzle there. But then the integrals that come out are always trig integrals. And the process of going back to the original variable requires you doing this thing where you draw a triangle and label the sides in terms of the variable x. I've taught trigonometry a few times at Santa Fe, and I'm always like shocked. And so I know that this step here, going from here to here, might be a little bit hard, depending on where you took trig. Like I said, I know the trig here at Santa Fe is not very good. So I'm going to move kind of slowly through this, and I want you guys to talk to me and let me know what feels weird. It's not your fault if you don't have a super strong trig background right now. I think of it as our fault here at Santa Fe. We just don't. But that class does not get the love it deserves. So it's super important that you communicate a lot with me, what's hard, what's not hard, what we need more time on, what we don't need more time on. That way we can move through this efficiently, but without leaving anything behind that you guys are unprepared to deal with. Everybody okay with this step? Are there any thoughts about this? Remember that secant theta is the reciprocal of cosine. So saying x equals secant theta is the same as saying x equals 1 over cos theta. So to pass from here to here, I'm taking reciprocals. You could, from this step, you could say theta is the inverse cosine of 1 over x, but I don't recommend it. You don't need it. Because I don't have any thetas. I don't have any thetas alone in here. I've got the secant of theta and the tangent of theta. And if you come back to this step and you tell me that this is the secant of the inverse cosine of 1 over x, well, it's true. It's really not anywhere near as useful as telling me it's just x. I would much rather you just tell me that it is x. So the important thing is that from this relationship, you can draw the triangle, because the triangle is what's going to allow you to actually get nice expressions here. The only case where you actually need to solve for theta is if you get out in your integral, if your integral actually comes out to just be like theta plus c, or theta squared, or 1 over theta, or something like that, then you would need to solve for theta, but that's very, very rare. Most of the time, you're going to end up with trig functions here. And I want to know what those trig functions are in terms of algebraic expressions involving x. So rather than going all the way and solving for theta, I would much rather you get to this place and then draw the triangle and then give me nice algebraic expressions. It's true, for example, that the tangent of the inverse secant of x is the square root of x squared minus 1. And I would much rather you write it as the square root of x squared minus 1 than the tangent of the inverse secant of x. Let's try a few more. I'll grab some from the textbook. We need to make sure we do a mix of definite and indefinite integrals. We can play with that. So I gave you guys this table, right? Remember from last Friday. This table I refer to as the Trig Sub Bible. If you see this, then you should substitute this because of this. I think the version of this I gave you wasn't quite as thorough, so maybe I'll run back through that before we do this next example. Okay. So make sure you get this nice and clear in your notes. You're going to need to refer to this as you do the homework. It's just the Trig Sub Bible. If you're religious, please don't be offended. It's not actually scripture. If your integral contains substitute this because this. All right, and here u of x is any linear function of x. All right. So u here, I'm going to write instead of x, could be like x plus 2 or x minus 1/2 or 2x. If your integral has something that looks like the square root of a squared minus u squared, then you should substitute u equals a sine theta. Because a times parentheses sine squared theta minus 1 a squared is going to be a squared cos squared theta, and the square root of that is nice. If your integral has a square root of a squared plus u squared, then you should substitute u equals a tan theta, because a squared times 1 plus tan squared theta is a squared secant squared theta. Again, whose square root is nice. And if your integral has a square root of u squared minus a squared, then you should substitute u equals a secant theta, because then your thing under your square root would be a squared times secant squared minus 1 which is just a squared tan squared theta. So in these things on the right-hand side, I've factored out the a squared, right? You'd have here a squared minus a squared sine squared theta, and you can factor out the a squared. Oh, I need to turn this one around. I'm sorry. Sine squared minus 1 is not cos squared. It should be 1 minus sine squared theta. Okay. Yeah, sorry about that. All right, so if u squared is a squared sine squared theta, then you would have a squared minus a squared sine squared theta. Factor out the a squared, and you have a squared times 1 minus sine squared. 1 minus sine squared is cos squared, so that would be a squared cos squared theta. And the same sort of thing follows all these. All right, so this is your guide. You look for stuff like this in your integral, you make the appropriate substitution, and then you use the Pythagorean identities to simplify. And as long as you chose the right substitution, these square roots will all clean up and go away. So let's try this guy. I want to integrate. I've got 9 minus x squared under the square root upstairs, and downstairs was it x or x squared? X squared. What is A here? So this square root looks like one of these to me, right? It's the square root of 9 minus x squared. So A, this guy, is the square of 3. So I want to substitute here x equals 3 sine theta. U is just x. A is 3. So then dx will be 3 cos theta d theta. Now I would think over here, okay, this means sine theta is x over 3. And remember, sine I can always understand using my SOHCAHTOA as the opposite over the hypotenuse. So I'm going to come in here and go ahead and draw my triangle right away because I know I'm going to need it at the end. The opposite side is x. The hypotenuse is 3. And then if I go to complete this triangle, right, of course this is a right triangle, I know that this squared plus this squared has to be this squared. So this guy has to be the square root of this squared minus this squared. So the missing side of my triangle here is the square root of 9 minus x squared. And that missing side will almost always be the expression that you're substituting into here. So that's my little substitution box. Yeah, almost always. Not always, but almost always. Sometimes we make these substitutions even if there isn't a square root. There are a few other occasions, but if it's following this pattern as straight up as this guy is, if it's coming straight from the Trig Sub Bible and it's exactly like that, then the missing side will always be that square root expression. Okay, now we plug in. 9 minus x squared is going to be 9 minus, and I'll write it all out carefully, 3 sine theta squared divided by 3 sine theta all squared, like this. And then I've got my 3 cos theta d theta, that's my differential, don't forget that. Forgetting the differential is murderous, ruins the problem. And now we just have to be careful. We just have to do all of our simplification. So downstairs here I'll have 9 sine squared theta. Upstairs there I'll have 9 minus 9 sine squared theta. Definitely cannot cancel these, right? First off, the stuff upstairs is under a square root. Second off, this is not a factor of the numerator. So no cancellation here, but this square root will simplify nicely. I factor a 9, and then I have 1 minus sine squared theta under my square root. And this piece becoming this piece, and this becoming cos squared, that's the magic. That's the whole reason we did this. So that numerator is going to become the square root of 9 cos squared theta, because 1 minus sine squared is cos squared. Downstairs I have 9 sine squared theta, and over here I still have 3 cos theta d theta. And the square root of cos squared is cosine. The square root of 9 is 3. There's no more addition or subtraction under here. It's all multiplication. So I can go ahead and take that square root. That's going to be 3 cos theta over 9 sine squared theta times 3 cos theta d theta. Now I've got a 3 here and a 3 here. That gives me a 9 upstairs. I've got a 9 downstairs, so the constants all cancel. And you get integral of cos squared theta over sine squared theta. How do we do this integral? Yeah, I treat it as cotangent squared. Very good. And then how do I integrate cotangent squared? Anybody remember this? It's a lot like tangent squared. Good, we rewrite it in terms of cosecant. What is the relationship between cotangent and cosecant? Yeah, it's just like secant and tangent. So cotangent squared is cosecant squared minus 1. And then what's the integral of cosecant squared? Almost. Yeah, negative cotangent. Very good. So just like regular tangent differentiates to secant squared, cotangent differentiates to negative cosecant squared. So the integral of cosecant squared is negative cotangent. So I get negative cotangent theta from this piece. And the integral of 1 d theta is theta. So now we're done with the integration, but we're not done with the problem, because I still have to go back to my original variable because it's an indefinite integral. Now, conveniently, I already drew my triangle, right? So there's a reason I like to get this out of the way up here. That way at the end, I don't have to like change my track of thinking. I just finish up the problem. So cotangent is the adjacent over the opposite, right? It's the reciprocal of tangent, so it's going to be this over this. And then theta I do have to write as an inverse sine. So the cotangent piece, that's negative this over this, square root of 9 minus x squared over x minus theta. And then from here, theta is the inverse sine of x over 3. And then your plus c is still there. So this comes from the triangle. And this is coming from here. I take the inverse sine of both sides to solve for theta. Since sine theta is x over 3, we know theta is the inverse sine of x over 3. That's kind of like the problems we did last week to introduce this, where you solve for theta. And that's it. This is a full-blooded example, right? This is all the stuff that you can expect to need to do in these problems. So take a second, make sure you've got all this stuff down in your notes. then look it over and see if there isn't anything that that feels shaky or weird or unclear that you'd like to talk about a little bit more. Thoughts on this? Anything? So the name of the game is to get rid of the square root. The real money step is here. The thing that lets us do that is the Pythagorean identity. So you need to know those cold. You also, I don't like the word memorize, but you need to know this table, right? You can kind of smell your way there by thinking about the Pythagorean identities, like, oh, which Pythagorean identity has a plus in it? That's the one for tangent, right? Tan squared plus 1 is secant squared. So if you see the plus under the square root, you know you're going to substitute tangent. And then these two, you have to remember which order the subtraction goes in each identity. 1 minus sine squared and secant squared minus 1. So if the constant comes first, and then you're subtracting your variable, that's going to be the sine substitution. And if your variable comes first and then you're subtracting a constant, that's going to be the secant substitution. But this you need to know. I won't be giving you this on a test. Of course, you're not allowed any notes on the test, so this you must know cold, as well as the trig identities. A second or two longer here for people to look at this and see if there are any questions they'd like to ask. Make sure you have all the steps clear in your notes.
Excuse me, sir.
Yes.
Yeah, the inverse sign, I'm talking about the bottom where you say minus square root 9 minus s squared over s minus inverse sign. So the inverse sign should be 3 over s.
Help me out a little bit. I'm having a hard time hearing you. Which piece are you looking at? Like, call this line 1.
The bottom, I'm talking about the bottom. The last line.
This line?
No, the bottom. Yeah. Okay, yeah, that one.
And you're asking?
Inverse sign, yeah, what is the inverse sign? S over 3. I think it is 3 over s if we look at the triangle.
Well, so the sine of theta is the opposite over the hypotenuse, right?
Yeah.
So the sine of theta is x over 3. And then remember the way the inverse sine works. This is not the negative first power of sine. This is not cosecant. This is the inverse function. So what I did to go from here to here, I'm glad you asked. So what I did to go from there to there, I'm going to remind you guys how this goes. So if sine theta is x over 3, then what you do is you take the inverse sine of both sides. Sine inverse of sine theta equals sine inverse of x over 3. And then the inverse sine of sine theta is theta. And that's what I was plugging in for right here. Right, so this theta right here is the inverse sine of x over 3.
Okay.
Where he's coming from. So it's not that that's the reciprocal. It's true that if I wanted to look at cosecant 1 over sine of theta, or the sine of theta raised to the negative first power, that would be 3 over x. But that -1 notation, you could also, another way to write this is arc sine, right? If you prefer the arc sine notation. So you would get theta is arc sine x over 3. So the -1 there isn't a power. Remember, it's the inverse trig function. So if you prefer to write it as arc sine rather than sine inverse, that's okay. But make sure you have clear in your head which one means which. So I see what you're saying. It's a reasonable concern. But here, this is correct.
Thank you.
All right. Any other thoughts or concerns on this, guys? All right, let's play around with a few more examples. Let's see, the ellipse is always fun. Well, let's save that. This looks okay. X over. We'll do one more indefinite integral, and then we're going to do some definite integrals, because I think the definite integrals are where we're going to need the most practice. All right. So here, the square root that I have that I want to simplify is this guy. And he has the plus in him. So this is like a u squared plus a squared, where u is just x and a is 2. So I'm going to substitute x equals 2 times the tangent of theta, which means dx would be 2 times secant squared theta d theta. And while I'm here, I'm going to draw my triangle. If x is 2 tan theta, then tan theta is x over 2, which is the opposite over the adjacent. So I draw my triangle. With the opposite labeled as x and the adjacent labeled as 2, which means that this piece is going to be the square root of x squared plus 4. So there's all my good substitution stuff. And now I get to plugging in. Dx is 2 secant squared theta. I'll put my d theta at the end there. X squared is 4 tan squared theta. And that square root is 4 tan squared theta plus 4. And then my d theta chilling. Okay, so the differential term I put up here to try and save a little bit of space. This square root is what I'm trying to simplify. To do that, I'm going to factor the 4 inside the square root. So I'll have 2 secant squared theta upstairs. Downstairs here, I've got my 4 tan squared theta. And then inside that square root, I'm going to factor a 4, and I'll have tan squared theta plus 1. Now tan squared theta plus 1, that's secant squared. You notice I'm not doing anything with these constants until after I simplify the square root. It makes life easier. Figure out what's going on with all the constants, and then we'll pull it out. So this tan squared plus 1 is secant squared. I had to factor the 4 inside the square root before I could see that, right? I had 4 tan squared theta plus 4. So I factor that 4, I'm still leaving everything under the square root, and that gives me the tan squared plus 1, which is secant squared. Now I can take the square root of 4 secant squared theta, and I get 2 secant theta. So altogether here I'll have integral 2 secant squared theta over 4 tan squared theta times 2 secant theta d theta. So downstairs I have 4 times 2 is 8. Upstairs I just have a 2. So a 1/4 will pop out. And then I get integral secant squared over secant. I can cancel one of those. So I'll have secant theta over tan squared theta d theta, like so. From here, I would recommend rewriting as sines and cosines. So I've got my 1/4 out front. Secant theta, that's 1 over cos theta. And then dividing by tangent squared, that's the same as multiplying by cos squared theta over sine squared theta. You can cancel one of the cosines. So I get cosine over sine squared. And there's more than one way to finish it from here. Anybody see anything that could work? So at this stage, I could do a z sub for sine. cos theta d theta is dz. So I'll get integral 1 over z squared dz, which is the integral of z to the negative 2 So he would integrate to negative z to the negative 1. So I'll have negative 1/4 times 1 over z plus a constant. I'm not sure if a double angle formula would be helpful there. The other option is to write this as cosecant times cotangent. That's the other thing that I see here. So 1 over sine is cosecant, cosine over sine is cotangent. So you could rewrite this as cosecant times cotangent, and that would also give you your integral. So if I go back to my thetas, I'll have negative 1/4 times 1 over z, which is 1 over sine theta, and then 1 over sine theta, of course, is cosecant theta. So you end up the same place you would if you rewrote that as cosecant times cotangent. And then before we can call it quits, I have to go all the way back to my variable x. So remember, we actually made 2 substitutions here. We did the trig sub and then the z sub. So before we can finish things, we need to use my triangle to figure out how to rewrite cosecant in terms of x. Cosecant is the reciprocal of sine. Sine is opposite over hypotenuse. So cosecant is hypotenuse over opposite. So this is going to be the square root of x squared plus 4 over x. So I'll have negative 1/4 square root x squared plus 4 over x plus c. Like this. So these aren't too bad, but they can get pretty long. In theory, you could find yourself doing some trig sub, and then that could lead you into a looping trig integral that requires IBP. Maybe somewhere along the way you have to do another U sub. So all the techniques that we're learning this semester, they can be tied together. And it can be quite a long process to get not just to an answer, but then to get from that answer all the way back to an answer in terms of the original variable. It can be quite tedious. But if you're patient and you follow your nose and you think about what steps would make sense given what you're looking at, there's nothing outrageous here. You do need to be 100% comfortable with section 7.2 though. Okay, questions on any of these steps? So let me come back to that line. Oop. So I'm thinking of secant over tan squared as secant theta times cotangent squared theta d theta. Oh, and I've got my 1/4 here also. All right, so I'm adding this in at the end. The secant theta hangs out. He's 1 over cosine. And tan squared downstairs, that's the same as cotan squared upstairs. Cotangent is cosine over sine. So that's cos squared over sine squared. So Colin, I'm just using the definitions of secant and cotangent. Secant is the reciprocal of cosine, and tan downstairs is the same as cotan upstairs. That's the definition of cotangent, the reciprocal of tangent. And then cotangent is also cosine over sine. So if you like, you can call those reciprocal identities. Really, they're definitions. Yep. Not a problem. Other questions on this? Any one of these steps feeling a little bit strange or need a little bit of explaining, or you just want to talk about it a little bit more? If not, I'm going to look for a definite integral example. So this one is fun. This is a neat example here, example 4. I'm not going to run through it because it's a lot like the very first example we did. When you first look at this, especially when you just learn trig sub, you want to go ahead and plow ahead with x equals 2 tan theta. But if you're sneaky, you notice this x upstairs. You don't need trig sub. This one can be done with a u sub. So watch out for this sort of trap. There are a lot of integrals that can be done both ways. This is a good example, just like the integral that I called a on the first page. This one doesn't require trig sub. So always look to see if there's a u sub or some easier way to do your integral before jumping in with the trig sub. We're not going to talk about hyperbolic substitutions. Hyperbolic trig is not an official part of this class. But example 6, this looks scary. Let's do this. So that's the integral from 0 to 3 square roots of 3 over 2. I'll write this down. X cubed over 4x squared plus 9 raised to the 3/2 power dx. At a glance, this looks much more intimidating than the last few problems we've done. First off, it's a definite integral. And what's up with this fucky upper bound? 3 root 3 over 2, I don't like that. Again, we don't have a square root here either. At least it doesn't look like it, but remember that the 3/2 power, that's the same as the square root cubed. So this is the same as the square root of 4x squared plus 9, all then raised to the 3rd power. So there really is a wonky looking square root down here. Another thing that's intimidating, this doesn't look like x squared plus a squared. And that's why I gave you that table in terms of u and a, where u is allowed to be any linear function of x. I'm going to really take my time on this one, and I want you to follow along very carefully. The numerator, I'm going to leave alone, but I'm going to rewrite the denominator. Four x squared is the same as 2x all squared. And the 3/2 power is the same as the 1/2 power cubed, which is the square root cubed. Now compare this to your Trig Sub Bible. Which is around here somewhere. if you wanted to, I could make this look even more like the line in the Trig Sub Bible by rewriting it as the integral from 0 to 3 root 3 over 2 x cubed over parentheses square root 9 plus 2x squared cubed dx. Do we see it? Here's a squared, here's u squared. So that is a square root of a squared plus u squared. It's just a little bit disguised. So your algebra skills need to be on point. So what am I going to substitute in this integral? What substitution, what trig sub am I going to do here according to the middle row of my Trig Sub Bible? U, which is 2x, equals a, which is 3, times the tangent of theta. That's the substitution. All right, this is a squared plus u squared. So I should let u equal a tan theta. A is 3, u is 2x. That's okay. So now taking differentials, 2 dx is equal to 3 secant squared theta d theta. Also here, because this is a definite integral, I need to change my bounds. When x is equal to 0, I'll have 2 times 0 equals 3 tan theta. In other words, tan theta equals 0. So theta is the inverse tangent of 0. Which is 0. And when x is equal to 3 times the square root of 3 over 2, you'll have 2 times 3 square root 3 over 2 equals 3 times the tangent of theta. The 2's cancel, you get 3 root 3 equals 3 tan theta. So that's the same as saying tan theta equals the square root of 3. Which means theta is the inverse tangent of root 3, which is pi over 3. This bound changing work will never get more complicated than this. But you'll see things like this, and it's not infrequently, so you need to be comfy with what's going on here. In particular, you need to be able to know what the inverse tangent of root 3 is, what the inverse tangent of 0 is. Your inverse trig skills gotta be up to snuff, which is why if you look in the review resources module in Canvas, I've got a few links there to help you practice your inverse trig. So my old integral ran from 0 to 3 root 3 over 2. My new integral is going to run from 0 to pi over 3. X cubed, well, I don't know, x here is three halves tan theta, because what I'm substituting is 2x equals 3 tan theta. So you can solve this for x. So x cubed is 3 halves tan theta all cubed. Downstairs, I have the square root of 9 plus 2x squared. Well, 2x is 3 tan theta, so that's 3 tan theta squared. And then that whole square root is being cubed. But I'm still not done putting in my substitution yet because I also need to put in my differential. If 2 dx is 3 secant squared theta d theta, then dx itself is 3 halves secant squared theta d theta. So again, take a second, make sure your notes have everything you need, make sure it's clear. This is no small amount of work. So this was dx. And I got it by solving this for dx. The whole 2x piece I replaced by 3 tan theta because that was the substitution I made. And the bounds changing work here was somewhat complicated. But the rules are the same. You take your substitution and you plug in the old lower bound. So when I plug in 0 for x there, I get 2 times 0 equals 3 tan theta, which means 0 equals 3 tan theta, which means tan theta equals 0. And then I take the inverse tangent of both sides to get theta is the inverse tangent of 0. Oh, well, the inverse tangent of 0 is 0. And precisely the same sort of work up here. When I plug my old upper bound into this expression, I get 2 times 3 root 3 over 2 equals 3 tan theta. The 2's cancel, and you get 3 root 3 equals 3 tan theta. Divide both sides by 3, and you get root 3 equals tan theta, or tan theta equals square root of 3. And then again, I take the inverse tangent of both sides. If tan theta is root 3, then theta is the inverse tangent of root 3. The inverse tangent of root 3 is pi over 3. And then these two pieces, they just come from plugging in. So now we're ready to go ahead and try this. Got integral 0 to pi over 3. This is going to be 3 halves cubed times tan cubed theta. I'm going to leave the top as it is right now, though. till we see what comes out from the bottom. I'll have another copy of 3/2 here. I'll move the secant squared upstairs. And then downstairs here I'll have 9 plus 9 tan squared theta under my square root. I can factor a 9 here, and then I'll have 1 plus tan squared. So it'll be 9 secant squared theta under the square root. Upstairs here I see a 3/2 cubed and a 3/2. That's 3/2 to the 4. So I have integral 0 to pi over 3. 3/2 to the 4th power. Tan cubed theta times secant squared theta all over. Downstairs here I will have the square root of 9 secant squared theta cubed d theta. And you can see things starting to come together. When you take the square root of 9 secant squared, you get 3 secant theta. So you get integral 0 to pi over 3. 3/2 to the 4 tan cubed times secant squared all over. The square root of 9 is 3. 3 cubed. The square root of secant squared is secant. Secant cubed d theta. Okay. So now I'll shuffle my constants outside. I've got 3 to the 4 over 2 to the 4 times 1 over 3 cubed. Integral 0 to pi over 3. 2 secants upstairs, 3 secants downstairs, so tan cubed over secant. Out front, those constants, 3 3's downstairs, 4 3's upstairs, so I'll have 3 over 2 to the 4 for my constants. 2 to the 4 is 16. Integral 0 to pi over 3. What do I do with this stuff? Tan cubed over secant. Oh, I can't close that. Damn. All right. What do I do with tan cubed over secant? Yeah, we can always try to rewrite this as sines and cosines, or I could hunt for some sort of Pythagorean thing. I could write tangent cubed as tan squared times tangent, and then tan squared I could rewrite as secant squared minus 1. Hope that something nice happens there. But for my money, I would just go ahead and rewrite this as sines and cosines. See what that looks like. So tan cubed, that's sine cubed theta over cos cubed theta. And then secant downstairs is the same as cos upstairs. So I can cancel one of the cosines. And I'll get sine cubed over cos squared. So I could rewrite that as tan squared times sine. That's not nice. Is that right? Sine cubed over. Yeah, this is tricky. This is tricky. Let's see. I would like to see more cosines going away. I see it. This is not easy to spot. Anybody got an idea? What if I rewrote it like this? And then one more sneak. Sine squared is 1 minus cos squared. So from this line, can anybody see what to do? How about this? Yeah, very good. Sub for cosine. I'll need to change my bounds again. When theta is equal to 0, I'll have 0 equals cos theta. Or no, theta is equal to 0. I'll have z equals cos of 0, which is 1. And when theta is equal to pi over 3, I'll have z equals the cosine of pi over 3, which is 1/2. So my new integral, I'll have a negative pop out from the differential, negative 3/16 integral 1 to 1/2 1 minus z squared over z squared times dz. The negative I already brought out. And then we can split that up. This is 1 over z squared minus z squared over z squared. I can soak that negative back inside by flipping the bounds over, which is nicer because right now the lower bound is bigger than the upper bound. And then this becomes z to the negative 2 minus 1. So I get 3/16 times z to the negative 2 becomes negative 1 over z. Minus 1 becomes minus z. And I have to evaluate this from 1/2 to 1. So this will be 3/16 times. When I plug in 1, I'll get negative 1 minus 1. when I plug in 1/2, I'll get -2 minus 1/2. So altogether, I'll have 3/16. This right here, -1 minus 1, that's -2. And then I'll distribute this negative, so I get +2 plus 1/2. So this is 3/16 times 1/2 is 3/32. And that's it. No, the negative came inside because I flipped the bounds. So it's a good question, Maggie. The negative here came inside when I flipped those bounds over. So here I'm using the fact that negative integral b to a is equal to the integral from a to b. Negative integral b to a equals positive integral a to b. All right, this is a long problem. This is about as bad as these get, which is good news if you think about it, right? These don't get any worse, and you can handle this. You can handle any of these trig sub problems. You're going to need to be very careful. I hope that that's coming through in the work that we did here. These require a little bit of love. They're not super easy problems. You can imagine if this was an indefinite integral, and I had to go back to my original variable, that would be a pain in the ass. So I'd have to chase back through both of those substitutions. But it's a nice thing that you change your bounds. You don't have to go back to your original variable. You're required to change your bounds in this class. It's not a matter of preference. You must do it. And the reason is for problems like this, because if you tried to solve a problem like this without doing that, it would be a tremendous headache. All right, how are we doing on time? I have a feeling we are over. Yes, we are. Shit. All right, I'm into my next class. It's time already, so I got to get out of here. Todd, oh yeah, if I haven't done that, I will do that very, very soon. Okay, thank you for the reminder. Yeah, if I forgot to upload last Friday's lecture, check my YouTube channel. I might have uploaded it but not linked it, but if it's not there, I'll get it in later today, I promise. All right, I gotta go, guys. If you want to talk more, come see me in office hours. Otherwise, just watch for that homework to drop. It's going to be dropping a little bit later today, and then get on it. If you need more time on last week's homework, submit an extension request, okay?